Okay, hello and welcome to part 3 of 20 integrals. So, the reason why I've just been going at a very slow rate of uh 5 integrals per video is really because I cannot talk for so long without my mouth going dry. So, mad respect to all my teachers who talk for 1.5 hours straight. Anyway, as promised in part 2, I am going to spend a bit of time going through integrals of this form. So these four standard forms I've just copied out from your formula list MF27, and you can just find them in the formula sheet. So I'm going to start today's video by going through integrals 11 and 12 that are of this form. And I've also decided that I'm going to, for part 3 and 4, I'm going to put the sources of these questions as far as possible so that um, you can reference them if you need to. Anyway, so our first integral for today is pretty simple. It is of this particular form here, and we are going to integrate this using the standard form. So recall that the standard form that we are interested in here, which of the four standard forms does this look like, people? It looks like we can integrate using the standard form as follows, right? 1 over uh, x squared plus a squared dx, this is equals to 1 over a tangent inverse x over a plus c. This is the standard form in MF27. Sorry for the ugly handwriting, but yes. Anyway, so the key thing here, okay, you need to know the coefficient of x squared here has to be 1. Okay, no matter what crazy thing the expression gives you, you have to make sure that this coefficient of x squared becomes 1 through some kind of manipulation. So I can manipulate this now, and in order to make it 1, remember I just want x squared. I don't want 9x squared, I just want x squared. Okay? And then in order to change the coefficient of x squared from 9 to 1, because x is in the denominator, I don't take out 9, I take out a 1 over 9 from the integral, which means that this next term, instead of 1, is going to be 1 over 9. And the numerator remains unchanged. So I have expressed it in this form. So in this case, a squared is 1 over 9. So what is a? A is just going to be 1/3. So I can integrate it. I can just write it in this form so that it's clearer for you. 1/9 is 1/3 squared. So now I have x squared plus a squared, and I can integrate using the standard form. Tangent inverse. This is tangent inverse. X over my a is 1/3. And obviously, we are going to need to tidy this up. So if you tidy up the coefficients, you will find that these two in front will just simplify to 1/3. And because this is x over 1/3, 1/3 is in the denominator. So this is going to be tangent inverse of 3x plus c. And that is all. So integral number 11, pretty simple. Okay, let's do a slightly more complicated now. Let's do a slightly more complicated one now. So this particular question is a bit more complex. It's particularly elegant, I feel, because of how tricky it can be if you are not careful. So this was actually from A level just the following year, 2009, and it was question 2 of paper 1. So it's still relatively early in the paper, right? So you aren't usually expecting integration to come out as question 1 or 2, but in this particular year it did. So this particular question was written as follows, okay? The question said, find the value of p such that this expression, and they give you a definite integral. P squared x squared here. So this was the question in that particular year. So you realize they only gave people 4 marks in this question. So it's essentially 4 marks. You need to integrate both sides. Now, common trap here. Attempt to integrate both sides at the same time. People, it's technically possible, it's technically mathematically correct, but unless you are 天才, please don't, okay? So let us first integrate what is easier to integrate first. General principle. So, which of these two integrals is easier to evaluate? Obviously, this one, right? Because this one is already in our standard form. In fact, this is in the standard form over here. It is, I have a squared minus x squared and my numerator is 1. So I am just going to use this form here, which is a ln, and it is going to be, so let me just find this integral first. So I'm going to copy this over, and this is going to be equals to, so if I use that standard form, I'm already in the form that I want, okay? So in this case, a squared is 4, so a is just 2. So it's just 1 over 2a is 1 quarter ln, and remember, even though in MF27 they put as curly bracket, you have to write with the modulus in your answer, okay? So please don't just copy from MF27 blindly, remember to put the modulus. Please make what I just verbally said as an annotation in your notes if you haven't already. Please do it. Okay? Done? Okay. So if we sub in 1 and 0, you will just get 1 quarter ln 3. So that's this part done. Now let us shift our attention to this part. Okay? Remember, key lesson I said earlier, your coefficient of x squared by hook or by crook has to be 1. What is the coefficient of x squared here? It's p squared. So I'm going to need to get rid of that, right? So let us copy this integral over. And in order to make the coefficient of x be 1 or minus 1, I'm going to take out a term, some kind of constant. Okay, so remember, definite integral, the bounds remain unchanged, my numerator is unchanged. All that I'm interested in is I want to change this to something minus x squared. So if I want to change this to minus x squared, means that I have to take out, it's in the denominator, right? So it's 1 over p. Okay, I know the p is in the square root, but I have a p squared in a square root. So just take out 1 over p, okay? And then, consequently, instead of 1, this particular term here is just going to become 1 over p squared. Okay? And then with respect to x. So, as a result, I can integrate now. I'm already in my standard form. I am in the standard form here, the sine inverse form, a squared minus x squared. So, just in these two examples already, I've showed you how to use this form, I've showed you how to use this form, I'll show you how to use this form. And honestly, if you can use this form, then you can use this form already. So I don't think I need to go through, or at least I don't need to search exhaustively for an integral of that last form for you. So if we integrate this using that standard form, this is going to be sine inverse, right? So my 1 over p is still outside. Yeah, 1 over p sine inverse of px, and my bounds. So if I substitute this in, you will see that I'm going to get 1 over p, and this will actually be sine inverse half. Okay, because I have 1 over 2p here, I have 0 here, so if I sub in, we will get sine inverse half, and that is going to be uh sine inverse half. You can press your scientific calculator. Remember last video I made a mistake. I go and put my scientific calculator in degree mode. Please, there's pretty much nowhere in H2 mathematics. I think there's nowhere in H2 mathematics that requires your scientific calculator to be in degree mode. Your graphing calculator doesn't have a degree mode. It's just in radians all the way. So please, ladies and gentlemen, at the start of the math paper, before you flip open the question paper, before you even turn on your GC, go to your SC, change your SC from degree to radian, okay? So, if you press your SC, you will get, I need to express it in terms of P, right? So, this will actually be pi over 6P. So, I have, this is my integral on the left-hand side, right? and then this is my integral on the right hand side. So what I want to do is I want to equate the two. So I want to say that 1/4 ln 3 is equals to pi over 6p, because what am I trying to do again? I'm trying to solve for p, find the value of p such as this. So if I rearrange, p is already the subject lah. So I'm just going to cross multiply. I will see that p is 2 pi over 3 ln 3. Okay, and this is already in exact form because this is an exact constant. Ln of something is also exact. Okay, so just because it's not numbers, it's still in exact form. Okay, it counts as exact form. So that is two of our integrals for today done. And that is it for those four forms given in MF27. So just remember what I've just taught you in the past 10 minutes or so. Whenever you are dealing with an integral in one of those familiar forms in MF27, please make sure that you actually have the coefficient of x squared be either 1 or minus 1. Okay? Now, the next one that I want to show you is actually another integration by substitution problem. So, you remember last video we did a lot of integration by substitution. Here's another one, okay? So the um question is as follows. This is a very, very old question. This I actually got it from the Hwa Chong December holidays package. Why on earth the teachers have access to such old questions is beyond me, okay guys? It's actually beyond me. But anyway, this is from RJC in 1993, and it was their prelim paper. Question 19. Okay, yeah, the O-level format was very different, such that you can get 19 questions in paper 1. And it says the integral is denoted by I. Okay, yeah, another hallmark of an old question. You realize that nowadays we rarely use the symbol I to denote an integral anymore. I mean, in America, they seem to like to use this I notation a lot, but we don't do that in Singapore as much anyway. So it says that I denotes this particular integral. It's a definite integral, and it's in terms of y. So it looks quite simple, quite benign, right? But if you think about it, this is not actually very integratable. So they say using the substitution y equals to sine squared theta, they want you to solve this integral. Okay, actually originally this was a show question lah, but I'm not going to copy that out because we're going to derive the expression anyway. So remember, integration by substitution, first step to do is to differentiate this substitution. So I can get 1 mark in the integration question from performing differentiation. So if y equals to sine squared theta, I want to find dy d theta. Now, I can treat this as power rule and chain rule, right? So if I bring the power down, I will get 2 sine theta. Then I chain rule this. I differentiate sine theta, I will get cos theta. So differentiate sine squared theta, I get 2 sine theta cos theta. So this means that dy, this thing here, dy, is equals to 2 sine theta cos theta d theta. Okay? So remember, for definite integrals, I have one less step because I don't need to convert back to in terms of the original variable. I don't need to convert back in terms of y. But I also get one more step because I need to convert these bounds over here, 3/4 and half. Okay, so now I'm going to go through my second step of converting the bounds. So when y is equals to sine squared theta, and sine squared theta, in this case y, I am going to take care of the upper bound first. This means that I will always use the principal values. Okay, I said this in the part 2 as well. Always use the principal values, always use the basic angle. So sine theta, I just take the root of sine squared theta, and therefore my basic angle of this is pi over 3. So for the lower bound, if sine squared theta is equals to half now. Sine theta, I take the root of that, is going to be 1 over root 2. And therefore, theta, I take the basic angle, press your scientific calculator, is pi over 3. Now, your scientific calculator will give you a bunch of random gibberish irrational numbers. Okay? I trust that having grappled with the lack of computational power of your Casio throughout Sec 3 and 4, you have realized by now that the way to stop your scientific calculator from giving you a bunch of not useful, irrational bullcrap is to just press answer divide by pi so that you get these two very, very nice numbers in terms of pi. Okay, but in the event that you have somehow made it through O-level additional mathematics without knowing this trick on a scientific calculator, well, you learn something new every day. Okay, so let us now get into the integral proper. So I'm just going to use I because the notation of the question wants me to. But yes, just use this very old question as a way to appreciate the beauty of old notation. So I will change my bounds, right? So my bounds have now been changed to my upper bound is now pi over 3. My lower bound is now pi over 6. Okay? Just, ayo, sorry, I go and joke with you all until I make a fatal mistake. This should be pi over 4. I'm so sorry, guys. Pi over 4. Sorry, I got carried away. I'll be more serious for the rest of this video. Anyway, so I'm now going to replace my y with sine squared theta. So this is now going to be 1 minus sine squared theta over sine squared theta. And is this an expression that you are familiar with? Yes, right? So now I'm going to replace my dy with this thing, 2 sine squared theta cos 2 sine theta cos theta d theta. Okay? And then, as I have said, this thing on top should hopefully be very familiar to you. That is just going to be cos squared theta over sine squared theta times this entire thing d theta. So I'm just going to skip a bunch of steps now, and I hope you can see that basically what is cos squared theta over sine squared theta? Cos squared theta over sine squared theta is cotangent squared theta. So this will be cotangent squared theta. What is the root of cotangent squared theta? Cotangent theta. Okay, what is cotangent theta? Cos theta over sine theta. Okay, so I know I've just skipped a bunch of steps there. I don't feel that it's worth writing it down because you should hopefully be well versed with this basic trick by now that you have known since Sec 3. But in case you don't, yeah, here you go. When in doubt with trick, right, please be stupid and do what I just did. You don't want to make careless mistakes and forget to cancel things or accidentally cancel things you shouldn't be cancelling. Anyway, hopefully it will become obvious that because I've simplified it until like that, this one and this one cancel. So I am left with an integral that looks like this. 2 cos squared theta d theta. Now, for me as a person, I'm very uncomfortable with having a constant inside my integral. So I'm just going to tidy things up now because it makes more sense to me this way. Okay, it's up to your personal preference if you prefer to do it like what I just did or not. But it doesn't matter, it's just because I'm OCD. So, we've gone through, I think, twice already in part 1 and 2, how to integrate sine squared theta, how to integrate cos squared theta using double angle formula. So if I use double angle formula, this is going to be equals to... Actually, no, I should have just kept my 2 in there. Because 2 cos squared theta is in the double angle formula. So if I just keep it as 2 cos squared theta, I am going to get... This will become sine 2 theta over 2 plus theta, correct, right? Let's check our double angle formula. Cos squared is 2 cos squared. Yeah, it's correct. So this is going to be pi over 3 pi over 4, and then now comes the difficult part of subbing in everything. So if I sub in sine 2 theta, sine 2 times pi over 3 is 2 pi over 3. Okay, let's just show every step because we don't want to make careless mistakes. So if you have to, please write more than you absolutely have to, waste more pen ink and be kiasu. Okay, you have the luxury of a lot of additional answer space. So 2 times pi over 4 is pi over 2 over 2 plus pi over 4. So if we sub that in, this is going to be uh sine 2 pi over 3 divided by 2. Sorry, let me just take my SC real quick and work that out. Yeah, I'm working it along with you guys. So according to our scientific calculator, hopefully you're pressing, I can't show you the SC press right now, of course, but hopefully you're pressing your scientific calculator with me. This is going to be root 3 over 4 plus pi over 3 minus sine pi over 2 divided by 2 half. Yeah, so this, if you press this, you press and then plus pi over 4. So this will give you root 3 over 4 minus half plus pi over 12. And actually, right, the original question, they said show that this integral I is equals to this. So they just want you to factorize the 1 over 12 out. Why they want you to demonstrate that you can perform set 1 math just for one additional line, I have no idea. But please don't go against the question. Leave it in the form that they want, okay? So we have two more integrals to get through today. The next integral that I want to show you, both of these are actually from more recent papers. So this is actually from a JPJC prelim paper. So both integrals 14 and 15, which I will spend the remainder of this video doing, are from JPJC prelim 2021. This was actually a paper 2 question. So two integrals, part A, part B. Now, part C of this question, I have actually showed you already. Where's that? Yeah, this last integral, the one that I ended off part 2 with, you remember this was a particularly difficult one because we had a lot of trick, we had a very tedious substitution, and I was showing you as well how to do integration by substitution for a definite integral, right? This was actually part C of that question. So this particular JPJC prelim question, right? Part A and B I'm about to show you, part C I've already showed you. Okay. Uh I'm not sure if I've said on the channel before on some of the other math videos, but typically the pure math in paper 2 will be harder than the pure math in paper 1. Typically lah. You can go and look at 2023 A level paper 2. There's a vectors question. I think there's a circle. Yeah, you can go and take a look at that. That's proof to you that paper 2 pure maths is really quite diabolical lah. So I will say a lot in the statistics videos as well. Once you get your paper 2, please do the stats before you do the pure math. Okay, get the 60 marks for stats, get a B for paper 2 at least, then only you go to the pure math, go to the section A, and then you salvage whatever you know how to do lah. Because trust me, right, half the things in section A you either won't know how to do or you will feel like that's the most diabolical paper you've set for in your life, even after you've gone through countless paper 2s, through TPE, prelim, etc. Okay, that's just the thing about H2 math. I'm bad at math too. So, uh, I'm sorry, I promise I'll be serious for the rest of this video. Let's be serious now, gang. Let's log in, okay? So, this particular integral is as follows. Quite a very, very simple one. In fact, I don't know why I'm putting it in this part lah. Maybe just to give you guys a treat since we've been doing so much techniques recently. Let's just go back to first principles. Let's do a simple integral. So even though I said this is simple, you might pause the video for a bit and think, wait, how the shit am I supposed to integrate this? Is it supposed to be partial fractions? Okay, number one, this thing cannot be split into linear factors. Okay? Number two, typically if they want you to use partial fractions, then like the very, very first integral we did all the way back in episode 1, they will already give you in linear factors. So the fact that they give you in quadratic form like that, right, means 通常 they don't want you to use partial fractions because it's not partial fractions above. Okay, so for this one, I'm going to want to show you, even though it's very simple algebra, it's a method I haven't showed you in episodes 1 and 2 yet. So in this part, I'm going to show you this new method, okay? What I'm going to do is I'm going to rewrite the numerator like this, okay? Watch what I'm doing. No. 2x minus 2 plus 1. Is that correct? Yeah, it is. You can check yourself and see that that simplifies back to x. So why have I chosen to rewrite it in this oddly specific way? Is because, right, you will see what happens is that now I have split the numerator into two terms. So originally I have just one term in the numerator. Now because I have two terms in the numerator, I can split this into two different integrals. So once again, me being me, I don't like to have a constant in my integral. Let's take that half out. And then and you will see that when I split it into two terms, two different integrals, it's actually a lot easier to solve. So you might be thinking, okay, I know how to solve this one in front. How the shit do I solve this other integral? Integrate what we know how to integrate first. Claw back as many marks as we can, ladies and gentlemen. So obviously, this one is just in the form, if you haven't spotted it already, is in the form f prime x over fx. So if this is our fx, then our f prime x, if you check, will just be 2x minus 2. So this is directly f prime x over fx. You don't need to uh, check, do any manipulation. And just remember, when you have this form of an integral, it is going to be ln modulus fx plus c. Okay? So we are going to write that in now. This is going to be half ln modulus x squared minus 2x plus 5. So I've written it as a modulus. I will go back to this point later, okay, on the modulus. Now, how do I actually integrate this? Now, the way that you simplify the denominator, this is a way of thinking that you may have forgotten from Sec 3 and 4. So think about it, right? In Sec 3 and 4 O-level A maths, if Sec 3U from 2 or 3 years ago saw this fraction, how would Sec 3U try to simplify it? Sec 3U, obviously, first thing he or she would do is to try and factorize this, right? But it can't be factorized. So what have you learned in A maths in Sec 3 and 4 that teaches you how to simplify expressions like that are unfactorizable? Completing the square. So don't forget these kinds of old tricks like that. You may be a new dog, but that doesn't mean that you can't use your old tricks. You learn new tricks, but you can still use your old tricks, okay? So if I'm going to complete the square on this one, it's going to be x minus 1 squared plus 2 squared. If you want to convince yourself, fine, let me reteach you Sec 3 math, okay? X squared minus 2x plus 5 is equals to x squared minus 2x plus 1 minus 1 plus 5. This thing here will give me x minus 1 squared. Minus 1 plus 5 is plus 4, so it's plus 2 squared. Okay? Yeah, that was really embarrassing. I can't believe I just had to teach your Sec 3 math. But anyway, I hope you get how to complete the square. And then this is what I mean about a minute ago when I said I will go back to the point on the modulus here later. Because, right, if you see from completing the square, what will sec3 u be able to tell you just from this completing the square expression? This one, this expression x squared minus 2x plus 5 is always positive. So, ladies and gentlemen, do I need this modulus? No, right? In this case, because I have ascertained that it cannot be either positive or negative, it's only one of them, I can safely and correctly write it in curly brackets, okay? Whether you will get penalized for leaving your final answer in this modulus form is up to the marker. For Hwa Chong and RI and what's the other school that's damn stringent about math presentation? Basically, for Hwa Chong and RI, yes lah. But please make it a good habit to be correct rather than just technically correct. Okay? So, what does this form look like, ladies and gentlemen? We covered it in the first two integrals. We started this video by promising that we will look at integrals in this form, right? This looks like a tangent inverse, isn't it? So, I can simply write it as follows. Understand? Good. Plus C. And are we done? Yes, we're done. Fantastic. So do you see how this looks like such a simple integral, but then it requires you to solve it by splitting. And if you think about it, right, if I didn't just show you how to write it in this form, would you have thought of writing it in this form, especially under time pressure? No, right? So this is the kind of thing that they can give you in a paper too, right? That will really trip you up. And you will be very, very good at statistics because stats is for babies. It's easy. Okay? So please, in a paper 2, do your stats first. Don't arrive at the stats section having been absolutely morally crushed by things like this. Okay? Last integral for today now. Part B of that question. So this integral that I just showed you was part A. This question is part B. So we have done integral like this before. Yeah, you remember this question? They say part 1, show that dtx something equals to something. Part 2, therefore find this. So this is the exact same type of question. Okay? I'm just revisiting this question type, not only for convenience because it appears in my list of questions with the previous one, but also because I think it's best to show you two examples of this same type. And also because we haven't touched integration by parts at all in this video. I have touched integration by parts already in episode 1. I have touched integration by parts in episode 2. Let us end this video off with an integration by parts question. Okay, so part 1 of the question says, find the derivative of this expression. Okay, now obviously we will be able to use chain rule on this. So if I chain rule this, tangent, right? If I chain rule it, I will just get secant squared of x cubed. And then the function inside x cubed is going to be 3x squared. So if you're OCD like me, you can just write it as 3x squared secant squared x cubed. Okay? I don't think I need to harp on this. This is sec 4 math. And then they say hence. Okay, so you need to use this. Find the following integral by integration by parts. Now remember LIATE. So I have a trigonometric function here. I have an algebraic function here, which is going to be my u. Obviously, this will be my u. And then this is going to be my dv or my v prime. So, ladies and gentlemen, if u is equals to x power 5, what is du? That's going to be 5x power 4, right? X5 or... Wait, did I copy the question wrongly? No. Okay. Yeah, so if x, u is this, du is this. Yeah, I'm sorry. Anyway, then if dv is actually sec squared x cubed. Okay, no. I'm sorry, I would like to stop here. Let me rewind a bit, okay? I'm so sorry for having led you down this little rabbit hole. But I think I figured out what's so hard about this, okay? Yeah, as I said, paper 2 pure maths is actually hard, okay? They they ask you hence find this integral, right? They want you to rewrite it as the following. Take a 1/3 out. Then only you can write x cubed, then 3x squared secant squared x cubed dx. Then only you get the form that they found in part 1. Okay, I'm so sorry. I was wondering why the question was like that also. But yeah, we both got confused together. Yay. Anyway, so now we know that this is going to be my dv, right? This is my dv. So my v is just going to be this expression. And then my u is here. So if my u is x cubed, then my du dx, or I prefer to write it as just du, is going to be 3x squared. Ah, okay, this is how they want us to solve the question. So therefore, by integration by parts, I keep my 1/3 out of my integral. It's going to be u v. V is tangent x cubed minus integrate v du. And do you see this expression recurs here? So we know how to integrate from part A because we are given that. So this is going to be x cubed tangent x cubed minus 3x squared. Oh no, I'm so sorry. This is not, okay? You need to know how to integrate this. So, do we actually have to do another integration by parts? I don't think so, because this is simply I integrate tangent. Okay, wait, I'm so sorry. Just let me do another integration by parts just to give myself peace of mind. I'm so sorry. I have confused myself as well as you. I'm so sorry. So now if this is my u and this is my dv, then I integrate tangent x cubed. But if I integrate tangent x cubed, that is just going to be something secant squared. Oh, yeah, we don't need to do another integration by parts. It's just going to be ln mod secant squared x cubed, because this 3x squared here and this x cubed here, this is f prime x tangent fx. So by that standard form f prime x tangent fx, I will just get ln of secant squared fx. Okay, it's a standard form. Let me just write that out again. Standard form is if I have f prime x tangent fx and I want to integrate this, this is equals to secant squared fx plus c. This is another standard form in your notes. Okay, so yeah, you can spare yourself the misery of doing one more round of integration by parts by just summoning that standard form and add that plus c at the end. Okay, so that is it for this installment of 20 integrals. We have 15 down, 5 to go, and I will catch you in the next part. Bye bye.